All right, so last lesson we had a question that put everything all together, where we were given an equation of a curve and we had to use the first derivative to find the stationary points. Then we found the second derivative so that we could find what the nature of the turning points, the maximums and minimums. Then we used the second derivative to find points of inflection, and then we had to test the points of inflection with the table to see if the concavity changed, and then we had to draw the graph. So those kinds of questions where you have to start with basically one equation, find stationary points, test stationary points, find points of inflections, test points of inflections, and sketch them. There's a lot of steps involved there, and it unfortunately can get even more than that. In this, we're only doing one question today.
Yes.
There's 2 pages of one question. Okay, because the curve that we were looking at in that example was just a very nice bendy curve. It didn't have any quirky parts to the graph. That's right. But what happens if we have a cusp or a vertical gradient somewhere, or discontinuous points? Okay, so there are other things that we need to look out for. And so in this exercise, this is a list of all the different things that you could need to do. It's not a checklist that you need to go do that, do that, do that. Most of the time the questions will be divided up into steps for you that will kind of lead you through it anyway, but things to keep in mind, okay? So when we're sketching a curve, it's always good to know your domain straight up, because that's going to help with any of the discontinuous points part, right? So try to find your domain, first of all. It says always do this first. Step 2, we can check for symmetry, whether it is odd or even or neither. That is by subbing in f of minus x into your function. If it comes out the same as your f of x, it means it's even. If it's not the same, but you can bring a minus out and then it's the same, that means it's odd. If it's neither of those things, then it's not going to be either odd nor even. Okay, the third one, we want to find intercepts. So find the y-intercept and all the x-intercepts, or all the zeros. Part B is to use a sign table to test what is happening to the sign in between those x-intercepts usually, okay? 4, we want to start looking for asymptotes, both vertical and horizontal. So vertical asymptotes, it says examine any discontinuities to see whether there are vertical asymptotes. And B, horizontal asymptotes, examine the behavior as x approaches infinity and negative infinity, noting any horizontal asymptotes. Then finally we get to some calculus where we want to use our first derivative. It says find the first derivative and any discontinuities of that derivative. So if our derivative is a fraction and something is going to be making the denominator 0, we could find a discontinuous part of our derivative. Okay. Part B of that is that we're going to test our derivative in our table of slopes to determine the nature of the stationary point and also the gradient of the rest of the curve as well. Step 6 is the second derivative. We can use that to find the concavity, obviously. Use the table of values to test the concavity to find any points of inflection and the concavity of the function throughout the domain. And question 7 says, any other features? It says a routine warning of any incompleteness, for example, trig graphs that repeat periodically. So just to keep an eye out for those kind of special cases. All right, so one question. This question is broken into the steps for us, so we just have to follow through what it says. So this is all about the equation y is equal to 1 over x bracket x minus 4. First thing, part A, probably no surprise, write down the domain of the function. What values can I have, or what can't I have, more specifically, for that equation? 4 and 0. Okay, the denominator is always factorized for us. So it cannot be 0, which means that x cannot be equal to 0 and x cannot be equal to 4. All right, part B. Use a table of test values to analyze the sign of the function. We've got quite a few different types of tables that we use now. So it's telling us a table testing for the sign means the x, the y, and the sign. Where have you been? Did you not need your stuff in period 6?
We had PDHPD.
All right, so in our table, we have the point 0, space, and then 4, space, values in between. So -1 for less than 0, between 0 and 4.
1.
I chose 2 because it was right in the middle, but you can choose something else. And above 4 is 5. Okay, for the 0 and the 4, the value of y is non-existent, which means I'm putting in stars or little stars in here saying they do not exist here. Now, grab your calculators out and start subbing in the other values. So -1. 1 over -1 bracket -1 minus 4 equals 1/5. Good. Change the number. You don't have to retype it. Put in 2. Very good. Sub in 5.
1/5.
1/5 again. Good. So the sign is positive. These are not slopes, so don't draw me slopey lines here. We know that it's positive there. It is negative between those two asymptotes. We'll get to that. And positive again here at the end. So that is telling us that y, those two discontinuous points, aka they will be vertical asymptotes, on the outside of those two asymptotes, on both of them, it's going to be positive. The graph is going to be above the x-axis. Between those two asymptotes, it's negative. So something's happening down below, possibly, kind of curvy shape down here. Okay, all right. So let's just write a little, what have we worked out from this? Y is positive when x is less than 0 and x is greater than 4. Y is negative, or this means below the x-axis, when x is between the 0 and the 4. Notice no equal to signs on any of those inequalities because of those asymptotes. So I've already been talking about it. Question C, part C. Find any vertical or horizontal asymptotes. Let's identify it. The vertical asymptotes are when x equals 0 and x equals 4. Okay, if it comes out in the original y equals equation that we can't have a certain value, it's going to be a vertical asymptote. But the horizontal asymptotes, I need to divide through by the highest power of x on my denominator. So before I do that, I'm going to rewrite my equation as y equals 1 over, expand the brackets, x squared minus 4x, so that I can divide through by my highest power of x on the denominator, which is x squared. So it's 1 over x squared on the top, over x squared over x squared is 1, minus 4x over x squared. 1x would cancel from the top and the bottom, but I still have 4 over x. Okay, now that I've got my equation in the right form, to find the find the horizontal asymptote, we need to find out what is happening as x is approaching infinity and as x is approaching negative infinity. And to do that, use this form of my y equation here, and anywhere where there is a fraction with x on the denominator, they're going to be becoming zeros. So for this, y is going to be approaching 0 on the top over 1 minus 0. Fortunately, there's a 1 on the denominator, which is, I need that not to be 0. So 0 divided by 1 means that that is actually approaching, y is approaching 0, otherwise known as horizontal asymptote at y equals 0. Okay, if my y values are approaching 0, that means that's my horizontal asymptote. Okay, part D. Show that the derivative of my equation is given by that lovely answer there. That means I can't use that answer, I just am trying to get to that. My original equation was y equals 1 over, and I expanded it out to be x squared minus 4x. Okay, by doing that, I'm going to be able to bring my denominator up to differentiate it. So that would be x squared take away 4x to the power of -1. Okay, now I'm differentiating the brackets using the rule. Y dash equals, the -1 comes down the front, it gets multiplied by the derivative of the bracket, which is actually 2 terms. This doesn't happen very often. I'm going to get 2x from the first term and minus 4 from the second term. So 2x minus 4, close bracket. Then the original bracket, the x squared minus 4x, stays in there, but I have to subtract 1 from the power. -1 take away another 1 will be -2. Okay, then I want to put that back into a form that's a bit more useful to me. That negative power, I want to put that back on the bottom of my fraction. So I'm going to have a negative, and I might expand that through. How about -2x plus 4 on the top over x squared minus 4x to the power of a +2. Now, in part E, looking ahead here, it says to find all the zeros and discontinuities of my derivative. To do that, I need to have my numerator and my denominator factorized so that I can read off any points. Okay, so I'm going to keep going with my derivative here because I know I'm going to need that on my next section. So to factorize the top completely, I could bring out a 2, and that would give me minus x plus 2, or let's switch it because it will look better, 2 minus x. Then on the bottom, even though that's in brackets, that is not completely factorized. Remember that we had an x in both of those terms there. If I want to factorize an x out of there, I will have to square it. So it will become an x squared bracket, x take away 4 in brackets squared. Okay, so now that's in a much better form to help me with part E. So E, find all the zeros and discontinuities. From the top of the fraction, that is where I find the zeros. Anything that makes my numerator 0 is going to be an x-intercept. So what can make this 0? When x equals 2, that bracket there. So I'm going to have a 0 at x equals 2. The discontinuities, too long a word. They are going to be at whatever makes my denominator 0, which is 0 from here and 4 from there, 2 of them. So at x equals 0 and x equals 4. Okay, so I've done the first part. I have found the zeros and the discontinuities. It then says use a table of test values for my derivative to analyze the stationary points and find where the function is increasing and decreasing. So this is a table using x gradient or y dash, and we're trying to determine what is happening with the slope. So we've got the three different values for x. So in order would be 0, 2, and 4, and we would need the gaps in between them. So space 0, space 2, space 4, and an extra space at the end. So that's very obvious to just be one, there's ones in between all of those. Nice whole numbers. For the x value of 2, that's a 0, which means my gradient is 0, and that is a flat horizontal slope. The discontinuities means the gradients don't exist there and there, which means the slope can't exist there and there either. So we need some little stars in there. Now to sub in to our gradient equation for the other one. So subbing -1 into here. So grab your calculators, 2 bracket 2 minus -1, close bracket, over -1 squared, 6 over 25. Lovely. Positive 1. Just tell you, it's too easy if I tell you all the answers. The next one is -2 over 9 and -6 over 25. Okay, so for slope, don't remember, the number's not important, it's the sign. So positive 6 over 25 means sloping upwards. Positive 2 over 9, sloping upwards. Negative 2 over 9, sloping downhill, and downhill for the negative 6 over 25 as well. So we can see in the middle here, this is a turning point. We have positive, 0, negative, so there's a maximum turning point right there. Okay, so we can see a maximum at the point 2. We're going to draw this in a minute. Let's find a y value to finish that point off. How will I find the y value? Into where? The original, way back up on, oh actually it's there. Sub into there, there it is. So subbing into there, and you will get -1/4. -1/4. That was also in our, we actually didn't need to sub it in because it was in this table. So now that we found it right there, 2 -1/4, so that was in our table from before. We do know as well that the curve, because the gradient is always positive here, the curve is going to be always increasing on the left-hand side of that first asymptote. And negative here means it's always going to be decreasing on that side of the asymptote. So let's make a note of that. It's increasing when x is less than 2, because actually increasing there and there, with the exception of that asymptote, that one broken point. So that is except yeah, sure. Decreasing everywhere where x is greater than 2, except for the other asymptote that gets in the way, which is at x equals 4. Okay, so if we go through all of the things that we've worked out along the process here, we should get a really nice sketch for part F. Sketch the curve and hence write down the domain and the range of the function. So here is my lovely big sketch. Okay, so starting with part A, we found the domain that x could not be equal to 0 and x could not be equal to 4. We later identified those as being vertical asymptotes. So let's put those in. Vertical asymptote at x equals 0 and another one at x equals 4. Okay. Table, part B, we had a table, and it told us whereabouts the curve was positive and negative. We could use a couple of the points in there to give us more of an idea if it helps you. So the first point, for example, we had was -1 and 1/5. So that means -1 is about here. It's going to be a little bit above there. We had at 2, -1/4. Probably getting a little bit ahead here, but that was our turning point, so that's an important one. 2, -1/4. That was another point we had in that table. And 5 up here was also at 1/5, so it's also above. Okay, part C, we had the vertical asymptotes, which I've already drawn on there, but we also found a horizontal asymptote at y = 0, so draw it across here. Horizontal asymptote at y = 0. Part D, we found the gradient so that we could find any discontinuities of the gradient and the nature of the turning point. So we found our turning point, which I've already labelled on there, and we found that it was a maximum, which does mean that the rest of the curve is going to be coming down on either side of that. We also knew that on the left-hand side of that x = 0 asymptote, my slope is increasing as I come towards there. So increasing means I'm going to be coming up like that, increasing, very steeply. On the right side of my x = 4 asymptote, all the gradients were then negative, which means it's going to be coming down and coming through that other point that I had over there. And that's it. Oh, wait, no, it's not it. Because the question says write down the range. Okay, so the range of the function is talking about the y values. For the two parts that are up here, they can go as far as they want up, but they're never going to get below the 0. So we'd say y is greater than 0. Y is greater than, not equal to, because it can't hit that asymptote. Or, okay, there's a second part of the graph which exists down here in the negative section. The highest y value is this point here. What was the y value? -1/4. Can it be equal to that -1/4? Yes, because that's where the turning point is. So it's going to be y is less than or equal to the -1/4.